Okay, we're going to keep talking about normal modes this time, but we're just going to use a numerical method. We're going to use the method of finite difference to really dig into range-dependent problems, at least approximately. But before we do that, I just want to summarize kind of conceptually, very hand-wavingly, what we've done so far. So the basic idea is that, we've taken our pressure field and we've said that it's going to be some sum over some modes times the range term, right? Range dependence. And the idea is that that you're decomposing the pressure field into all these mode shapes. These mode shapes were very intuitive when you think about all the classic, vibrational problems in physics. And so that's, really the name of the game here, is to understand that it's really the pressure field being expressed as a sum of these modes, okay? Now, what have we done so far? Well, we started with the ideal waveguide, and that was simply where we had p equals 0 at the surface, p equals 0 at the bottom, and we just had these, very easy to fit mode shapes in there. And we said that it was isovelocity, isospeed, same sound speed everywhere in our waveguide. Now, one thing we didn't talk about is you can think of many kind of riffs on that, and the classic one is the hard bottom waveguide, idealized waveguide, where you have P0 at the top and then dp dz equals 0 at the bottom, right? And in this case, you're going to have mode shapes, again, that are going to be really just going to change the one term in the mode shape. And here, same thing is isovelocity, isospeed waveguide, right? So covered those pretty quickly. And then we got into the Pecker's waveguide, and this is the fluid waveguide over a fluid half space. And we went through the solution to that in a couple different ways. Here we have pressure release, and then here we had these, the pressure is continuous, the velocity, the z velocity is continuous. Oops. So we had these important boundary conditions, and we found, the mode shapes, something like this. Right, and again, we had isovelocity sound speed profile, and then we had same thing in the bottom half space, homogeneous sound speed everywhere. And to simplify our lives a little bit, we had this alternative representation, at least of the field in the water column, where we still had the pressure release, but then we decided to draw an effective depth here, h sub e. And if this is isovelocity, and we don't really worry too much about the bottom, we can kind of see, well, these mode shapes in the water column are the same as if you had some sort of effective mode shape down to the effective depth, which is the very simple trigonometric function mode shape, right? So we had this alternative representation of the field in the water column, and of course at the effective depth, p equals 0. And then lastly, we came up with this generalized solution. And this is for the stratified ocean, in the sense that we have these layers, Z0, Z1, dot, dot, dot. And in these layers, we had some depth-dependent sound speed profile that we discretized, into each layer, okay? And the basic idea was in each layer, we have a PDE, right? And they're connected by the boundary conditions, right? So in the same way in the Pecker's waveguide, we have the boundary conditions here that connect the PD in the top to the bottom and that drive the total solution. When we have these multi-layered waveguides, we just have a whole bunch of those, right? Now that's totally overwhelming, but of course, by using transforms, we can just turn those into a system of algebraic equations. And now those equations are just linked by, you know, they're linked algebraically, I guess you could say. And we rearranged that and framed it as an eigenvalue problem. So in other words, we had AX equals B, and we said let's find the lambdas such that A minus lambda, the identity matrix, X equals 0. And you know, the analogy here is that, or not the analogy, I guess the take-home message here is that the eigen vectors are the mode shapes. And the eigenvalues we saw when we applied this method. Oops, getting too close to the bottom here. To the Pecker's waveguide, or to a two-layered waveguide, the eigenvalues are really the poles, or they're the wave number, right? And so we had all sorts of methods we can imagine all sorts of methods for finding these, right? Root finding, if we're looking at the determinant of the matrix, or any other numerical methods in terms of finding eigenvalues. And so we're going to get into that a little bit later on. But really what we want to go to this finite difference method is so we can deal with range-dependent problems. And finger settings, wow. Getting too close. Okay, range-dependent. Great. Okay. And so we're going to apply these finite different methods to normal modes and see how far we can get. So I'll do a quick rundown of the finite difference idea. So we have our modal equation. Where we have psi dz, psi is a function of z, plus omega squared, and we have some now depth-dependent sound speed, right? That's our k squared, and kr squared. Okay. So we're saying that our field psi is going to be a function of z, and here, just to be clear, I think I've been a bit glossy with this in the past. It's a displacement potential. And it's doubly transformed. So in the past, I would write this as psi omega kr, right? But I'm just going to drop those because, you know, I'll break my hand otherwise. So the idea with finite difference is to replace these with discrete things, okay? The differential. And so what we want to do here is use Taylor expansion. Well, I should capitalize that. Poor Taylor. Taylor expand d by dz. So we're going to apply that to everything, and so we can look just some j step away. Now we're talking about discrete steps here, where j is a small step in z. So we write the Taylor expansion down. Oops, one too many. Plus dot dot dot. And the primes here indicate derivatives. And the trick here is just to drop the higher order terms and rearrange. So drop the higher order terms because they're too hot. And rearrange to get the first order derivative is approximately equal to, okay, and this is basically from the definition of a derivative. I'm sure you recall this from first year calculus, right? It's all we're doing here, okay? So we can improve that a little bit by doing the order h squared approximation, in which case we get, there's our first order in h, okay, using our wave equation, right? And now we want to differentiate backwards. And by the same logic, we're going to have our Taylor's expansion. And by the same logic of combining the two, get order h squared j minus psi, psi j minus 1 over h omega squared over c squared j at that layer kr squared h over 2. Okay, so we can combine this one with this one, and I think left a j out there. So we can combine this equation for the forward differentiation with the backward differentiation, and we get the centered differentiation, which we'll call the centered difference, which comes out as two psi j plus psi j plus 1 all over h squared. Okay, so that allows us to turn our continuous problem into a discrete equivalent. So we can just simply sub those things in. We have psi j minus 1 plus minus 2 plus h squared omega squared over c squared at zj minus kr squared times psi j plus psi j plus 1 equals 0. Now j is equal to 1, 2, dot, dot, dot. We have n layers minus 1. Okay? Now, at the boundary, we can represent our boundary conditions in a few different ways. But for the continuous problem at the boundary condition, the boundary, we had this functional form, which I'm going to introduce and explain. F at the top or at the bottom, and then the mode function, the modal form of the function at the top, plus G rho dz. And these are the angle-dependent impedances. Which are very convenient because they allow, so this is a convenient form. Oh, yeah, okay. Convenient form. Because you can allow elastic bottoms. More complex bottoms in general, okay? And we got to make this equal to something here. Okay. So if you want more on this, we can actually, let's just discretize this part. So this is still in the continuous. This is the continuous version. Let's write the discrete version of this at the top and the bottom. And I'll go to the next page. So we'll have ft over gt times psi naught plus 1 over rho psi 1 psi naught h omega squared c squared 0 at 0 kr squared psi naught h over 2 oops equals 0. So these are just using the doubly transformed field at the layer 1 and in layer 0, right, for the top. And at the bottom, psi n in n layers. I think I used n previously, but okay. 1 over rho times psi n minus psi n minus 1 over h minus omega squared over, and here I'm going to use d in the sense that the waveguide has a depth d, so that's kind of from the continuous C evaluated at D within the layer N. Okay, so I just kind of wrote those down, but I will say C Appendix 2, Chapter 5 of Jensen. If you're a real detail-oriented person, go ahead and check that out. But you know, just wanted to jump to the conclusion here. Hope that's okay. So our main equation here, I'm going to label 1. That's a discrete version of our continuous modal equation, and we have this version at the top and the bottom. And now let's rewrite 1. And we're going to rewrite it in basically in putting together terms for psi j minus 1 and psi j plus 1 and psi j, of course. Okay, so we're going to have 1 over h rho psi j minus 1 plus minus 2 plus h squared omega squared c squared zj minus kr squared over h rho times psi j. And then we're going to have 1 over h rho psi j plus 1 equals 0. And so basically the idea now is that you can imagine at each, we have our layered waveguide. We're going to have j minus 1, j plus 1, j plus 2, etc., right? Now we can essentially write this whole thing as a function of kr squared times some vector of psi equals 0, where psi is equal to the vector psi is equal to psi 0, psi 1, psi 2, dot, 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 psi n minus 1, psi n, right? So psi 0, and now we can have, you know, all the way down to and the idea here is now that A, right, is going to be a matrix representation, and you can imagine we can find the eigenvalues of A, right? And the eigenvectors, and those will be approximations of the mode shapes. Okay. So our A is going to look something like D naught, E naught, 0, 0, dot, 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 you know, each row. So obviously the top row, we're going to have special circumstances because of our top equation. And we're going to have E1, D1, E2. And then we're going to have E2, D2, E3. And that continues all the way down. This tridiagonal matrix. And then we'll have En minus 1, Dn minus 1, En, and at the bottom we'll have En, Dn. And clearly I just need to extend this. I was optimistic in how small I can make this thing. So there's our matrix A. Now if we go back to our equation here, what are those tridiagonal entries going to actually look like? So we can do some simplifying. DJs are going to be minus 2 plus h squared over omega squared over c squared evaluated at Zn, minus kr squared, and that's all over h rho, right? So that's from our psi j term. And then at the top, we're going to have d naught minus 2 h squared omega squared over c squared at z naught minus kr squared plus these mysterious kr squared impedance terms. And at the bottom, we'll have dn minus 2 plus h squared omega squared over c squared evaluated at Zn minus kr squared, and these impedance terms, just leave them at that. And then ej everywhere is 1 over h rho. Okay, so that's what our matrix looks like. And this is this is like a normalization factor here, and you can tell that it importantly it contains the thickness of the layer, right? So don't know if I ever defined that at the beginning. I don't think I did. Wow. Okay. Now, what about these ratios of F over G. So for pressure release, F over G goes to infinity as psi naught goes to 0. So the first row and first column can be deleted. For the bottom, and we'll do a hard bottom here, F over G is independent of KR. So now all we need to do is solve the eigenvalue problem. And we have, not only do we have a tridiagonal matrix, saying, you know, there's zeros everywhere else. So there's zeros here, right? So we really just have these three lines down the center of the matrix, down the diagonal of the matrix, +1 and -1. But it's also symmetric. So we have a symmetric tridiagonal matrix, and there are many routines. This is where something like a software library in MATLAB is very helpful. Okay. And as I was saying, so we're going to find n eigenvalues. These approximate the modes. And in general, you know, you can imagine that if you're trying to approximate a mode, that you have good spatial resolution of the mode shape, it's no problem. When you get to very high order modes, they're going to be poorly resolved. And these, I'm going to say high order modes with respect to H are poorly resolved. Something to keep in the back of your mind. To normalize the modes, right? We need to satisfy that the integral from 0 to d, that's the water depth, of the nth mode over the density is equal to 1. So a few different ways to do that. But we can calculate a normalization constant accounting for the bottom. So the strictest way. By integrating over the mode shape, over the density, but including our boundary terms. Evaluated at the range step, which we're considering. Okay. Another alternative is that we can normalize numerically. An easy thing to do. Now, that gives us the mode shape in a all water with a hard bottom waveguide. What about if we want to add an interface, like a sediment interface? What do we do then? Well, okay, we can approximate the interface condition. What do we need? What's the physical boundary condition? So to add, oops, a non-boundary, I'm going to say, right, interface. In other words, what do I mean by a non-boundary interface? Well, discontinuity in the sound speed. Remember with the Peckris waveguide, we added a fluid bottom. It had a density, it had a sound speed, it was a fluid. We wanted it to represent an actual seabed. But the main difference was that this, the sound speed was discontinuous. Okay. So this is at D. We need the derivative. Oops. d psi dz, 1 over rho water equals 1 over rho basement bottom d psi dz. So how do we approximate that? Well, psi n minus psi n minus 1 over hw. We'll approach d from below. Kr squared psi n hw over rho w. Hw is the spacing on the water side. And that's going to be equal to the approach from the other side, from the sediment side. N plus 1 psi n over h bottom now. Sound speed approaching from the positive side. Density in the bottom. Okay, and just CD plus or minus is the limit value of sound speed approaching from plus or minus direction. So we can rearrange that, and we want to get it in a similar form where we can plug it into, we want to rearrange this equation so we can plug it into our matrix, right? So we want to separate the n minus 1, the n plus 1 term. I really should have used J here. My apologies there. So we can rearrange that. We get, so, uh-oh. Oh, I'm on the eraser. I'm not going to edit that part out either. Keeping it light here, folks. So we're going to rearrange this equation to plug into our matrix A. So we'll have psi n minus 1. Actually, you know what? I'm gonna switch to J here just to really bother everyone. H W rho W plus minus yeah, psi J omega squared over C squared at D minus KR squared psi J H squared W over 2, and this whole thing over HW rho W plus a minus psi J again omega squared over C D plus squared, oh, don't forget the squared, minus KR squared, oops, J, H squared at the bottom over 2, and that whole thing over HB rho B. Okay, and then we're going to have our psi J plus 1 HB rho B equals 0. J is location of interface, as opposed to the generalized J I had before, and as opposed to the N which I had for my bottom-most layer. So now A is going to look like this. You're going to have your stuff on the diagonal, you have your zeros, and then at interface depth, you're going to plug in your EI minus 1, DI, EI plus 1, and they're going to look like this. Your DI is going to be equal to HW, H bottom, omega squared, HW rho bottom over CW squared. Here I'm just using CW to be just above the interface. CB is going to be just below the interface. Should be rho W. CB, I better write that out. God, if I don't. D coming from there, and CB equals CD coming from below. Okay, continue this equation. Okay, and all of that is over HW squared, HB, rho B, HB squared, HW, rho W, okay? Our EI to the minus 1 is going to look like 2 times HB, rho B, rho B, HW squared, HB, rho B plus HB squared, HW, rho W, and our EI to the plus 1 is equal to 2 HW, rho W over HW squared, HB, rho B, HB squared, HW, row W. Okay, so you plug that row, you basically just take these, you plug them in where you want your interface. So more or less now we have a little bit of a recipe for solving the mode shapes in a totally generalized fluid environment. And we could even go to elastic if we want to learn more about those angular dependent impedances, F and GB. But now I'm going to just say, here's a little, what are we actually going to do with this? And why is this so powerful? We can go to range dependent problems. So like, how do we do that? And let's just do a little recipe for normal mode code using finite difference. Well, first thing we want to do is make our environment. So we can have our range and depth. Alternatively, we could have range and depth in the non-polar, non-azimuthal symmetric coordinate system. We change those into our indices that we're going to sum over, I and j, if you will. So now our continuous variables are all going to become discrete variables. Z, Zj. We're going to discretize our sound speed profile. And for density, we're going to, let me go back. So depth, of course, defines our grid everywhere, right? And let's just say, so this is going to be our range, I, and j is our depth. So we've defined our depth everywhere, and now we want to define our sound speed everywhere in range and depth. We also want to define our density everywhere in range, in depth. And we want to define some attenuation everywhere in range and depth. And just to be clear, we can take attenuation in the water column 0 for most things, and attenuation in the bottom, you know, we can kind of choose depending on what kind of bottom, but let's say 0.2 or so. Okay, so now we have everything in terms of I and j, the indices, and we have, you know, matrices which define our environment. So this could be some sound speed profile up here, increasing down there, right? And now we can actually change it in range, okay? Now what we want to do is we can figure out where our interface is, right? So we want to define this interface index. So we go from a depth to an index, okay? So put that in our recipe. We're going to define that interface index in I and j, okay? So we make our matrix A. So this is all step, this is all step one, sort of step one, making a discrete environment. Step two, make A and add the interface term. Okay. Step three, solve the eigenvalue problem. Okay, now I'm going to say some maybe outdatedly using the Eig function in MATLAB. Of course, you may use whatever you like, and there are probably some a host of good tools there. Now, the important thing is we're going to have n eigenvalues, and we want to only use the ones that are physically possible. So only accept positive eigenvalues between limits omega over the max of C and omega over the min of C, right? And these are these are modes that physically propagate, right? So you have quite a few left over. Then you want to sort. So you want to sort the eigenvalues. Oh, I should write this all out. Sort eigenvalues from biggest to smallest and normalize eigenvectors. Okay? And then you can take the first m modes from that list. Take first m eigenvalues that correspond to those first m modes and output as kr squared. Then step to next range and repeat. Okay? And at the end, you're going to have kr as a function of range and m, mode number, right? So for example, if you take the first 10 modes, you're going to have kr for all your range steps, 10 different values. And then you can add, well, you can combine with mode shapes. So you're going to have, say, the first m, so then you have the m modes at each range step as well, and you can combine with the kr and compute the entire field. So that's it. That's the very useful bit of code. If you can successfully put that together, then you'll have a bit of code for approximating the field from a variety of sources in an arbitrary waveguide, and quite a powerful little way to compute the field quickly. Okay, that's it for now.